Just put this on. Right, ladies and gentlemen, let's continue with chapter 11 on heat exchangers. In this chapter, is it on? Working. Yeah. In this chapter, we have done, let's call it, 2 parts so far. The first part was just an introduction to heat exchangers and the different types of heat exchangers. And then we've applied what is called the LMTD method to a few problems. And with the LMTD method, normally the heat exchanger is being solved by saying that the heat transfer rate is equal to the overall heat transfer coefficient multiplied by the area multiplied by delta Tm. And if the heat exchanger is not a counterflow heat exchanger, then a correction factor F is needed. The thing with the overall U is it actually takes together or integrate the heat transfer coefficient on the inner tube and the inner heat transfer coefficient in the outer tube. The heat transfer coefficient. So it makes things easier for you if somebody gives you the overall heat transfer coefficient and the surface area, because if you've got UA, then there's not much more to calculate. So that is the approach of following the LMTD method. But I'm going to show examples to you where I'm going to give you a problem, and then you're going to see, but I cannot use the LMTD because there's not enough information. And the only way to do it is to do it with iteration. And unfortunately, the iteration, if you do it like that, is not like some of the previous problems where you've chosen a property and it wasn't really that sensitive of the property. In most cases, it is actually very sensitive. So it takes quite a long time to do the iteration. Another method that has been developed is called the effectiveness. This is effectiveness number of transfer unit methods. So that is an alternative method that can normally be used if you do not have sufficient information to get the LMTD. And this is actually quite a fundamental method. It starts by defining the effectiveness of a heat exchanger as the actual heat transfer rate divided by the maximum possible heat transfer rate. The actual divided by the maximum possible. Now, what does it really mean? Well, let's look at an example of temperature as a function of X. Normally, we will have a stream with a high temperature, and that point will be fixed, and we will have another stream at a lower temperature, so that point will also be fixed. Normally, typically, if it's a single phase fluid, this temperature is going to decrease like that, and if this is also a single phase fluid, it's going to increase something like that. Okay, so this is the cold stream and that is the hot stream. Now, it's very simple to see, but if you take into consideration for a heat exchanger, this is the cold fluid and that is the hot fluid, that the maximum possible delta T would be that temperature difference. Delta T max. Okay. Delta T max would be possible if, for example, the characteristics of two things, the mass flow rate and the Cp of this stream, is of such a nature that a temperature, that it is going to do that. If this temperature, inlet temperature, is equal to the inlet temperature of the hot stream, it would mean it is the best that the heat exchanger can do. Do you understand that? Cannot transfer, delta T cannot be more than that. We can, of course, have the same for the hot side in terms of this temperature of this line going to let me just draw it like that. So delta T max would then be equal to, so if that is in and that is out, and that is in and that is out, then delta T max would be equal to T of the cold stream inlet temperature minus temperature of the hot stream in minus the temperature of the cold stream in. That would be delta T max, always. You see that? Okay. Now together with that, we're going to look at the terms of typically the hot stream. The hot stream would consist of the mass flow rate of the hot stream multiplied by the Cp of the hot stream multiplied by the inlet temperature of the hot stream minus the outlet temperature of the hot stream. Okay, I've used E. Let me rather use out there and rather in there. Otherwise, I'm going to mix my nomenclature. And so that would be T hot in minus T cold in. Okay. In and out and in and out. Let me not mix the nomenclature. There you are. You all happy with that? So this is typically what happens with the hot stream. With the cold stream, something very similar. It's equal to the mass flow rate of the cold stream, the Cp of the cold stream, and the temperature difference of the cold stream. Now what we're going to do is, these two terms, we are going to refer to that as the heat capacity. So that is equal to CH, TH in minus TH out. And this one would be the cold capacity, the cold capacity rate multiplied by TC out minus TC in. Therefore, C in general is equal to the mass flow rate multiplied by Cp. It's just taking those two terms together. Okay. Now coming back to this case where we've got this. If you go and look at this, and if you go and do an experiments, and you can do numerical analysis, and also the technique that we're going to do now is, if you go and look at the two streams, okay, the stream with the lowest value of C will have the highest delta T's. So that is going to be the one that changes the temperature the most. The lower the C, the more it will change its temperature. Now the other two possibilities that we haven't now mentioned is that what if we've got a phase change in one of these two streams. So if we've got the case of a phase stream, then the heat transfer rate in the hot side would be equal to the mass flow rate multiplied by the change in enthalpy. And it can be the change from a saturated vapor to a saturated liquid, or it can just be the enthalpy at 0.2 minus the enthalpy at 0.3. So you need to have the enthalpy values. Or on the cold side, it can be the mass flow rate on the cold side, or that's the hot side. Again, maybe HL minus HG, something like that. Okay. Now for these two cases, if you go and look at this capacity, the heat capacity rate, call this the heat capacity rate. This gives us an indication of if you've got 1 degree Celsius in temperature change for what will happen to the MCP. So if you go and look at this carefully, you will see that the C value for these cases are infinite. Okay, they've got an infinite C because the CP value actually doesn't exist during two-phase flow. We only use the CP value in a single-phase fluid. So if we now think of this, then we have two possibilities. The one can be that the maximum heat transfer rate is equal to the C value of H, which is Cp, multiplied by that temperature difference, which is the maximum temperature difference, Th in minus Tc in. Okay. So that temperature difference is the maximum temperature difference, Qmax. So the one possibility is that it is on the cold side. The other possibility is that it is on the other side, the C for the cold side. Th in minus Tc in. Okay, so there are two possibilities. Okay. Now, these two will give different answers. But one of them is going to give a higher answer than the other one. Which one is it going to be? Okay. Because for both of them, we use this delta T. Okay. The one that's going to give the highest heat transfer rate is the one which has the highest value of C. So, we need to get C max. So C max is either C minimum or C cold or CH. And just by looking at the values, we can choose the C max value. So therefore, in general, we can say that the maximum heat transfer rate is equal to C max, the highest of the two, multiplied by delta T max. The maximum heat transfer rate is equal to one of the two streams with the highest C multiplied by the highest possible delta T that you can have, that is C max. So that's the first term that we need in our effectiveness equation. Okay. Now in your textbook, we have previously started with, or we did the derivation of the LMTD, how the streams changes, etc. We're not going to go through all the detail again. Let me just see if I can get this thing to work. Okay, so there's the mathematics. So if you go through the mathematics, you will see that some of these terms start to appear, and in terms of then calculating the effectiveness, you start ending up with equations like that. Okay. So it starts with the equation of the Lin. With the temperature differences, you will see a UA there, and then at the end, after this derivation, the typical equation of 1 minus the exponent of UA surface area C minimum multiplied by 1 plus C minimum divided by C max divided by 1 plus C minimum divided by C max. Okay. So don't go and write it down. Okay. In your textbook, and this is typically the effectiveness for a parallel flow heat exchanger. And you can go and do it for the other heat exchangers also. The thing that I want you to look at is that the NTU is now appearing. NTU, the number of transfer units, which is equal to the total heat transfer coefficient multiplied by the surface area divided by C minimum. So therefore it is equal to U multiplied by AS multiplied by M dot Cp minimum. I hope you can relate to the other chapter that we did, where I've told you how important this value is. In the previous chapter, typically, this was the heat transfer coefficient. Now we just have the total heat transfer coefficient. Previously, it was HAS divided by MCP. And that was the NTU, and I've told you it's very important, that value. Always try and go and calculate it because it says something. Don't just put it into the mathematics and you come up with the answer, because then you're not going to have good insight in the answer. So this starts appearing, and then the other thing is that per definition, just to make things shorter, is C is defined as C minimum divided by C maximum. And the result is now that this derivation actually shows, and you can go and do it for different types of heat exchangers, that the effectiveness is a function of the number of transfer units and C. So the number of transfer units is equal to the heat transfer coefficient, surface area, mass flow rate, Cp. Which one of that? The one which is the lowest. Okay, and the value of C. And C is equal to C minimum divided by C max. C minimum is the smallest of the two streams. That's all. It looks a little bit complicated, but let's see if we can do an example. Excuse me. And make things more clear. So there we've got table 11.4. Okay, I'm going to show it to you now. Okay. There's table 11.4. Unfortunately, I think it will be difficult for you to read it. So please go to your textbook. Excuse me. There it is, and let me see if I can make it a little bit larger. No, it doesn't want to. Okay. But take a look at it, and you'll see typically the results of 3 different heat exchangers. The first one is the double pipe, in which we've got the parallel flow heat exchanger and the counter flow heat exchanger. Then there's the shell and tube with different passes, and then the cross flow. And then there's one there at the bottom, which you cannot see, unfortunately, but I'll say something about it just now. So, what we can also do is, those can be plotted like that. So in the plots, which is now figure 11.27, you'll see that the plots are giving the effectiveness as a function of NTU for different values of C. And C is equal to C minimum divided by C max. Okay? Now typically look at the one on the left and at the top. It is a parallel flow heat exchanger. Can you see? Just look at the arrows and you'll see that the flow directions of the inner stream and the stream in the others are the same direction. Okay? So if you look at that and you want an efficient heat exchanger, what are the things that you need to look for? Okay. You'll see firstly that if C minimum is equal to 1, okay, it's that line there, what will the efficiency be of that heat exchanger? About 50%. Okay. And it almost doesn't matter about how high the NTUs is. From an NTU of 2 to 6, it will be a 50% effective heat exchanger. So you can do whatever you want. You're not going to improve it. Okay? If, however, is the C values, the C minimum is equal to 0. Now, when will C minimum be equal to 0? C minimum is equal to, when C is equal to C minimum divided by the C maximum. Okay. When will that be equal to 0? It will be equal to 0 when we've got a high value there. When do we have a high value? When we've got a two-phase flow. Okay. So then C will be equal to 0. Now if we look at the zero line, you see there's the zero line. Oops, let me see. There's the zero line there. You can see that you can get to an efficiency of about 90% if the NTUs is about 2.3 or something like that. You can go to 90%. You see that? Okay. Now, here we've got the counterflow heat exchanger. Now the first thing that you should notice is where previously you've got this line of an efficiency of 50%, you don't have anything like that there. Okay. So it is clear that the counterflow heat exchanger is much more effective than the parallel flow heat exchanger. These are for the shell and tube, 2-pass, 4-pass, etc. And this is for a cross-flow one. Cross-flow one, and there you will see some dashed lines there. And many students want to know, but what are those dashed lines for? And that is the case for, if you go and read in the text, that is for the unmixed heat exchanger. Let me just make sure. Yes, so the dashed lines is for unmixed heat exchanger. Let's do an example. To apply the effectiveness NTU method.